Well, let's solve a system another way. Here, again, we have two equations in two variables, but we can solve this one by substitution without graphing. Okay, so to solve this one by substitution, remember for substitution we need one equation that has one variable isolated. So that is done for us here already, and so this parentheses now is as good as the y. It's exactly the same as the y. So we could go to the other equation and find y and rewrite it with the y replaced with this parentheses information. So substitution, I'm just going to abbreviate the word substitution. We are going to take 2x plus 3 and stop at the y and replace the y with this information here, x plus 4. And then continue the equation equals 7. We just rewrote the first equation but replacing the y with this parentheses. Substitution. Now we're going to solve this equation for x because this has only the variable x. Okay, so distribute to remove the parentheses. 2x plus 3 times x is 3x plus 3 times 4 is plus 12 is equal to 7. We're going to combine like terms. 5x plus 12 is equal to 7. We're going to subtract 12 from both sides. We have 5x is equal to negative 5. And that gives us x is equal to negative 1. Divide both sides by 5. X is equal to negative 1. Alright, now we're going to substitute again. Okay, so now we have a value for x. So we could go back to the earlier equation and substitute for x. Now we could use equation 1 or equation 2, it doesn't matter. This one looks easier to me, so I'm going to, so y is equal to x plus 4. Y is equal to, stop at the x and replace with negative 1 plus 4. Y is equal to negative 1, sorry, that was a 4. I was thinking instead of writing what was there. Negative 1 plus 4 now is 3. Now, all of this work produces an x value and a y value. Okay, so the solution to the system is the ordered pair, x value negative 1, y value 3. Okay, we want to test those to see if they work. Okay, so let's see, 2 times x, that's 2 times negative 1, that's negative 2. Plus 3 times y, that's 3 times 3, that's 9. So negative 2 plus 9 does equal 7, that one checks. So let's check it here. The y value 3 is equal to x plus 4, negative 1 plus 4. 3 is equal to negative 1 plus 4. That works as well. So we can say that it checks in both. So we know it's a good solution. Right, so let's solve a system by elimination. Alright, so substitution is good when one equation has one variable isolated. Elimination is good when both equations are in standard form. So these two equations are in standard form. ax plus by is equal to c. Now what we want to do is to add to eliminate a variable. Well, nothing happens here. If we add 2x and x, we get 3x. We don't eliminate the x's. 5y and y, we get 6y. We don't eliminate the y's. So we're allowed to multiply an equation by something to make the opposites we'd like. Okay, we want to add opposites to eliminate a term. So if I just look at the x's, I'd say, well, what would it take to eliminate 2x? I'd need a negative 2x. So I can multiply both sides of this equation by negative 2. Remember, that's a rule of equations that says if we do the same thing to both sides, well, we haven't. We still have the same equation with a different look. So when we distribute here, this gives us negative 2x and negative 2y, and on this side it gives us negative 6. Alright, so now this one changed to look like this. We're going to bring this one down. This is the one we didn't change. We're going to bring it down unchanged to add these two together. 2x plus 5y is equal to 9. And that causes the x's to eliminate. That zeroes out the x's. That's what we had in mind. Add the y's together. Negative 2y plus 5y is 3y is equal to negative 6 plus 9 is 3. Divide both sides by 3, and we get y is equal to 1. Okay. Now we can take the y value, 1, back to the easier equation, x plus y is equal to 3. Replace the y with 1. X plus 1 is equal to 3. Out of room here, but we're going to subtract 1 from both sides. And here I'm going to write x is equal to what? 3 minus 1 is 2. Now y is equal to 1, x is equal to 2, and that gives us a solution for the system. X value 2, y value 1. Now remember, we want to check to make sure that that works. So we're going to take the x value 2, y value 1 here to both original equations. 2 times 2 is 4, plus 5 times 1 is 5. 4 plus 5 is 9. That one works. So let's check it here. X plus y is 3. 2 for x, 1 for y. 2 plus 1 is 3. That one works as well. So we know that that is a solution of the system. Okay, now we want to quickly talk about special cases when solving by elimination or substitution. Okay, earlier we saw special cases when graphing. We know that parallel lines on a graph have no solution, and we know that same lines on a graph have infinitely many solutions. So what does that look like when we use elimination or substitution? Okay, special cases means that sometimes we get results like this. 2 equal 2, negative 9 equal negative 9, or 0 equals 0. All of these are true. So any true result when the variables disappear, and any true result, we call that an identity, and what it means is that we have infinitely many solutions. So a true result, or an identity, means that the equations actually would graph as the same line. Okay, we don't have to see the graph to know that this means we have infinitely many solutions. The other special case is we're trying to eliminate variables or solve for one or the other, and we get just constants again, but this time they're not true. These are all true. These are not true. 2 equal 3, 8 equal 9, 0 equal negative 5. Those are all false. So any false result, which we call a contradiction, that means there's no solution. Okay, so in graph form we would see those as parallel lines, but we don't have to see the graph to know that this kind of special case, a contradiction when solving by one of these methods, still means no solution. Okay, that would mean parallel lines. We don't have to see the graph of that to know that this result means no solution. Okay, true results, infinitely many solutions. False results, no solution.